Hello, my friends. Welcome to discussing chemical reactions using collision theory. Today we're going to talk about the need for collision for a reaction to happen, the role of the energy in collisions, as well as the orientation of the molecules when they do collide and how important that is. Awesome. Let's get started. So the first thing is that we actually need a collision. And to think about why, imagine when reactants come together, they're either going to trade atoms and form new stuff. They're going to transfer electrons. They're going to share electrons. They're going to be, ions are going to stick together. In any of those cases, a base requirement is those two reacting things have to come in contact with each other to have a reaction. So that's what we need for a collision. Now, to help illustrate that kind of visually, I put together this quick reaction. It's hydrochloric acid and phenolphthalein in this bottom well plate, and I'm going to drop in some sodium hydroxide. Now remember, phenolphthalein turns bright pink in the presence of a base. So each drop as it goes in, you'll see that flash of pink pop up. And right now you see there's this little space here where the sodium hydroxides hit into the water. The edges of it have reacted with hydrochloric acid, neutralizing the hydrochloric acid, but leaving a bunch of base left over, which makes the phenolphthalein pink. Now, as the hydrochloric acid around it collides with the edges, watch what happens to the size of these pink blobs in there. You can see how that hydrochloric acid is colliding. It reacts as it collides and slowly eats away at that extra base, neutralizing it and leaving the acid behind and turning the phenolphthalein from pink to clear. So again, collisions have to happen. Reactions can only happen in that interface between the two reactants. So wherever the base was touching the acid was where the reaction was happening at. This next one we're going to talk about is the role of collision energy. Now, when we examine the number of collisions that are happening in a chemical system, we find that the number of collisions is absolutely enormous, but the reaction rate is a lot less than the number of collisions. So we started thinking, well, why aren't all collisions a successful reaction? And what we came up with was the idea that you have to have a certain amount of energy, a certain intensity or violence of collision to create the reaction. So many collisions weren't energetic enough, weren't moving fast enough to actually cause the reaction. And the reason you need that energy is in order to break bonds in the reactant molecules and then form bonds in the product molecules. So to break those reactant molecule bonds, you're going to have energy to smash them and push the atoms apart from each other. Now this energy comes from the kinetic energy of the particles as they collide. So if they don't have enough kinetic energy, then they're not going to be able to break those bonds and form new ones. This energy is referred to as the activation energy. And of course, collisions with less than this energy cannot form chemical reactions because they can't break the reactant bonds. So in this video, I wanted to show you what happens to our speeds. So right now we have a gas floating around in here. Its speed is about 22 degrees Kelvin, so it's really, really cold. And we can see our distribution of energies here looks like this. So you've got a spike here and it goes down like this. So again, here's our speed on this side of the axis. We could change this word speed with kinetic energy, but you can see that at really low temperatures we get this bunching of tons of molecules have very similar speeds right here in the middle. Now what we're going to do is we're going to heat up the bottom plate of the box, and we're going to heat it up to about 50 degrees and see what happens. And notice that when the particles hit the bottom, they suddenly speed up. And we're speeding up now. We're up to 35 degrees Kelvin. We're at 40 now. And notice what's happening to our curve. Instead of being so spiky, it's actually spread out some. And what we have is a curve that looks like, like this. So this is at low temp. And now let's heat this thing up a little more. Let's take it up to 125 degrees and see what happens. This is at medium temp. And we're getting up to 105 now. 110. Now look what's happened to our distribution of speeds. It looks more like this now. Notice how it goes from being all of them going really slow and very similar speeds to now there's some going faster. But notice in here, even with that said, this one little guy is going super slow just by chance. There'll always be some going slow. So as we increase this again up to a room temperature of 298 degrees, you'll see all these guys as they hit the bottom, they speed up really fast. But we're up there now, and now our distribution looks more like this. So this is a high temp. Notice when you increase the temperature of a sample, its distribution of molecules, the average speed gets faster, and you get this over here, this idea of having lots of them that are going really, really fast. Now on here, if we had made a mark and we said, okay, hey, you know what? To get the reaction going, our kinetic energy has to be at least this much. What we would find is at high temperatures, all of these molecules would be able to react. So every time a collision happened with these molecules, there'd be a reaction. At this medium high temperature right in here, we'd say, oh look, only these couple molecules would be able to react. Anyone else can't react. So you can see here that by having a higher temperature, more of the particles are in a wider range here. Have gotten over the activation energy barrier there. So just to really clarify here, so we start out with our reactants here, right? This is NO plus CO2. We have this activation energy barrier of breaking bonds, and then it dies back down as we form bonds. And we get here CO plus NO2. This is that activation energy barrier. You got to get over it. Whoops. You've got to get over that in order to have the reaction. And only, remember, so if this is a KE and a number of particles, at low temps, it looks like this. It's spiky at low. Almost all particles have very low kinetic energy. And at high temp, it smooths out like this. And again here, if this is our cutoff, here and here, all these guys can make it over. Very few of those guys make it over this activation energy barrier. This is a fast reaction. This is a slow reaction. And that's because of getting over this energy barrier here to get to the other side. Interestingly enough, if this is exothermic, which it is in this case, this additional delta H of energy can actually provide the next molecules with a jump over that. So this reaction, once it gets going, can speed up because it may heat itself up, which is kind of a cool thing to do. Now, the last thing that's important for the collisions is, well, first of all, they have to collide. Secondly, they have to collide with enough energy to overcome that bond energy in the reactant molecules, the activation energy. The next thing they have to do is collide in the correct orientation. To clarify that, let's take a look at this. Here's our molecule. So here we have carbon here, and we have two oxygens. So that's CO2, and we have NO, so the red's nitrogen, oxygen, NO molecule. If they were to collide with each other with enough energy, bam, they bash into each other. That bashing in right here weakens this bond in between them because it tends to knock this bond apart. So the collision does that. And then the other thing that happens that's really critically important is nitrogen subtracts electrons from oxygen. Now, what that happens, this nitrogen atom starts pulling electrons towards it in this direction. And what happens is that weakens the bond here because it pulls electrons out of that electron density, making this bond weaker. So as this bond gets knocked out, it's also being weakened by the pull of electrons to nitrogen. So this is a new bond is forming. So instead of having to completely break this bond, it's actually being weakened by this new bond being forming and pull electrons out of it. And the result is NO2 and CO. This was an example of a successful collision orientation. Nitrogens and oxygens broke and was able to reform the bond. Let's look at one that wasn't successful. So we have our CO2 still here, CO2, and we have our NO, except now the orientation, it happens to come in so that it's oxygen to oxygen. So when this collision happens, this bond is going to get destabilized by the collision. This part is going to be true over here as well. The problem is this other part isn't true. Nitrogen's not pulling electrons out, so this bond doesn't get further weakened by that. And even if it is really weak, there's nothing for it to react with. It's not going to stick with the oxygen here. So the result here is a bounce instead of a reaction. So we need, not only do we need a collision, and a collision with enough energy, but we need a collision where the molecules are lined up properly so that the reacting atoms can actually break a bond and form a new bond at the same time. Let's do a quick recap. We got to have particles collide with one another. You have to have them collide with sufficient energy, and they have to be oriented so that the new bonds can form as the old bonds are broken. If all three of those take place, you have a chemical reaction. If any of them aren't consistent or aren't present, then you won't have a chemical reaction. All right, my friends, thank you very much for listening. Have a good day.